Okay, so any questions first about any of the material we had covered in the previous lectures?
Hocam şu power yazmıştık ya hocam. Average value.
The average power.
İşte orada hani omega üzeri 4 yazıyor. Her bir frekans için mi yoksa envelope mu?
Well, you see, whatever wave you have, you can always write it as a superposition of waves of different frequency. And they're called the different components. So a wave has different components having different frequencies. For each component, the power is given by that expression over there, which we had derived. For example, that was, I think it was the dipole radiation, right? Dipole, and also for the magnetic dipole radiation. They have similar expressions. So if you, whatever the time dependence of the electric or magnetic dipole you have, so you can always, just Fourier theorem tells us that you can write it as a sum or an integral, let's say a sum of frequencies of different frequencies. Each one of those components is radiating that much power. The total power radiated will be again just the sum of the power radiated by each one of the components. So in that example, we were considering the refraction of the sunlight, why the sky is blue, for example. The sunlight has many different frequencies. Each one will be driving the electrons, the charges in the atom at their own frequency. So basically the motion of the charges, mainly the electrons, will be a complicated motion, but nevertheless it will be a sum of those frequencies that are contained in the light from the sun. Now today we will be looking at a different problem, so-called the radiation back reaction. Now the basic idea is that we had already seen that if, for example, if there's a dipole that is changing with time, or in general if there's any charge that is accelerating, if you get accelerated charges, they will be radiating electromagnetic waves. And we had also seen that these electromagnetic waves, they carry energy. So let's just imagine a particle, a charged particle, let's say, which is under the influence of some external force. Now this particle will be accelerating, and if it was neutral, let's just compare two cases. One, we have a neutral particle under the influence of an external force. It will be accelerating, and from the work energy theorem that you are familiar from your first year, the work done on this point mass will be equal to the change in its kinetic energy. So this is for a neutral particle. Now let's just imagine an almost identical particle under the influence of exactly the same force, same external force, but this time charged. So again, we know that the external force will be doing some work on the particle, but this time that work will be converted into its kinetic energy, plus, since it's radiating energy in an electromagnetic form, plus the energy radiated by the electromagnetic waves. So basically, the change in the kinetic energy of the charged particle, we should expect it to be less than the change in the kinetic energy of a neutral particle under the influence of exactly the same external force. Because in the case of the charged particle, some of the work done by the force is converted into electromagnetic energy and it goes to infinity. Not all of it becomes the kinetic energy of the particle. Okay, does that sink in? Do you agree?
Peki o yüklü parçacığın potansiyelleri nasıl?
I mean, let's say that all those potential energies, we are considering the forces corresponding to those potential energies. So all the forces will be doing some work on the charged object or the neutral one. So the basic idea is under the same external forces, the change in the kinetic energy of a charged particle in a given time will be less than the change in the kinetic energy of the neutral particle. Because some of the energy given to the particle is radiated away. Okay. Well, that is basically the idea. Let's ignore the self-force that the charged particle exerts on itself. Well, does it exist is another issue, but that is where we will be heading to. We will say that if there is a charged particle, we are assuming that there are no external electric or magnetic fields. Or if there are any external electric or magnetic fields, we are considering them as a part of the external force. But no, we are not. There are no external electric or magnetic fields. Only the electric and magnetic fields created by my charge. All the other forces are, let's say, mechanical. So that they act the same on a neutral particle and also on a charged particle. The same force is acting on both of them. Even under these circumstances, the kinetic energy gain of the charged particle will be less than the kinetic energy gain by the neutral particle, because some of the kinetic energy gain will be radiated away. So we say that the charged particle basically creates a force on itself because of its electromagnetic fields. And what we will be trying to do now is to calculate this force. Now, of course, first we need to know the expression for the radiation field of this charge. Now, we had already studied in some detail the electromagnetic field of a moving charged particle. We studied explicitly what happens if the charged particle is moving at constant velocity. For an arbitrary motion, the electric field will be given by Q over 4 pi epsilon 0, R minus R prime, divided by, well, let me define a new vector first. Delta is R minus R prime. So the electric field will be Q over 4 pi epsilon 0, delta over delta dot U cube C squared minus V squared U plus delta cross U cross A. And U vector is given by C delta hat minus V. And the magnetic field is given by 1 over C delta hat cross E. And keep in mind that all these, the velocity and the R prime is the position of my charged object at the retarded time, and V is the velocity at the retarded time, A is the acceleration at the retarded time. So this, to calculate the electric field at the point R at the time t, we need to know the position of the particle at the retarded time, its velocity at the retarded time, its acceleration at the retarded time. So this is the exact result for an arbitrary charge doing arbitrary motion. Now, you see, if you look at the various terms in this expression, let's start with this one. Well, this factor is of the order of 1 over delta squared as you go away from the charge. So this is a 1 over distance squared, let's say. This is 1 over distance squared, so this term over here, U doesn't have any distance dependence, let's say. So this term is 1 over the distance squared. That is the term that reduces to the static electric field. And we said that that is not radiation. That is localized close to the charge itself. It doesn't go to infinity. Well, a nice example in the in your book is the example of flies following the rubbish truck. So there will be these flies moving with the rubbish truck. They will be just moving around. So those are these terms. They don't leave the truck, but there are some of the flies will just go away. So those are what we call the radiation field. This is our radiation field. And, well, we are basically eventually interested in the radiated field that goes very far away, so we need to calculate the pointing vector. Pointing vector is 1 over mu 0 E cross B. This is 1 over mu 0 C E cross delta hat cross E. Or this is equal to 1 over mu 0 C in the delta hat direction E squared minus in the E direction delta hat dot E. This is my pointing vector. Now in the radiation zone, in the faraway zone, the radiated electric field, as we said, it is just the second term over there. It is Q over 4 pi epsilon 0 delta over delta dot U cube delta cross U cross A. And you see, since it's the cross product of the delta vector with some other vector, it is perpendicular to delta. So for this case, for the radiation electric field, this delta dot E is 0. So in the faraway zone, we are very far away from the charge, the pointing vector is just given by 1 over mu 0 C E squared delta hat. It's basically moving radially outward.
Bu hocam çok uzak noktalar için.
Yes. So the thing that we are kind of trying to do is we are trying to calculate this back reaction to some approximation. There will be a few approximations we are actually doing over here. But to calculate the force, we are mainly looking at the power of all the forces acting on my charge. So that is what we would like. We are trying to calculate how much the energy of my object is changing with time, but that the change in the energy of my object is nothing but the power delivered to my object, and the power is determined by the net force acting on my object. That is what we are trying to do. This will be related to the change in the energy of my object due to this radiation of energy. Well, let's see, it's in the delta hat direction. You see, if you imagine it, this is what we will be imagining, how we will imagine it. This is my object. At the retarded time, it is over here. Now, at the time t, it is over here. Now, what we will be doing is mainly considering the retarded time. This will be my sphere. On this sphere, at the time t, the pointing vector is away from the TR. This is my delta hat vector at that point. Well, does it go in every direction? Well, let's see, let's look at the electric field. You see, if the electric field is non-zero in every direction, then it will be moving in every direction. But let's look at what the E square E is. We had already seen in some examples that the electric field, the radiation is only in the direction perpendicular to the acceleration. So for example, when we were studying the electric dipole radiation, in the simple case of these 2-point charges, time-dependent point charges along the z-axis, the radiation field had this sine theta dependence, which basically told me that there is no radiation in the plus z direction, there is no radiation in the minus z direction. And the maximum radiation is in the xy plane. So it doesn't radiate in every direction. There are some preferred directions for radiation. And that is perpendicular to the acceleration vector. Well, let's look at this one. This is equal to q over 4 pi epsilon 0 delta over delta dot u cube u delta dot a minus a delta dot u. Well, let's remember what u was. This is u. Now I will make a simplifying assumption. I will assume that v at tr is equal to 0. So basically, it's at rest at tr but accelerating. This just kind of will simplify the derivation. If this is the case, u is just c times delta hat, and the radiation electric field is q over 4 pi epsilon 0 delta over, well, delta dot u is just delta now, c times delta, over c times delta cube u delta dot a minus a times c delta. This is equal to q over 4 pi epsilon squared c cube 1 over delta squared. U is c delta hat delta dot a minus a c delta. These c's will cancel one of these c's over here. This will be q over 4 pi epsilon 0 c 1 over delta. Let me take a minus sign out. A minus a dot delta hat in the delta hat direction. Well, what is a times delta hat? So this is the component of a in the delta hat direction. We are multiplying it with delta hat, so a, and subtracting it from a. So this is perpendicular to my delta hat. So this is the component of a perpendicular to delta hat. So if delta hat is in the same direction of a, the component of a perpendicular to delta hat is 0, so this is 0. This basically tells me that there is no radiation in the direction of A. In the arbitrary case also. So this is just a complicated way of writing that we have this sine theta over r dependence, sine theta dependence. Now this is basically a sine theta in some direction. Or irradiation squared is q over 4 pi epsilon 0 c squared 1 over or a over delta a sine theta over delta squared. Now, what is this theta? Let's look at over here. Let's say at this point, this is the direction of acceleration. This is my theta. And the pointing vector, remember the pointing vector had this expression over here, 1 over mu through c e squared delta hat. Well, we already know what e squared is.
Hocam şimdi bu retarded time'da parçacığın hızı 0 dedik.
Yes.
O zaman nasıl ivme söylüyor?
Let's remember 109.
Kuvvet varsa ivmeleniyor. O zaman hızlanması da gerekmiyor.
Let's imagine this way, this example. There is a force in that direction, right? A constant, or let's look at this example. There's a constant force downward, right? Let me throw it up. At the top, is it at rest? Velocity is 0. It is accelerating. At the next instant, it won't be at rest, but at that instant, it is at rest. So as you said, it is accelerating. So in the next instant, it won't be at rest. Its speed will not be 0. But at that instant, its velocity is 0.
Elektrik alana dalga fonksiyonuna benzemiyor. Dalga oluşuyor mu? Ya da ben mi?
Okay, let's see if there is actually a wave over here. You see, it depends on what A is. So you want a harmonic wave? Well, let's say A of t is equal to sine omega t. A of tr will be sine omega t minus r over c. Sine omega t minus kr. So here is your wave. Look at the electric field. The A has this harmonic behavior. Well, if you look at the electric field, where is it? The radiation zone. So it is proportional to A. This is the sine omega t minus kr. Well, there is also this term, by the way. It's not just the harmonic, its amplitude is getting smaller and smaller. But imagine this is not definitely a plane wave. It's a kind of a wave, it's moving, it's spreading, so its amplitude is getting smaller and smaller. But just let's imagine, we know where the TV transmitters are in Ankara?
Ne tarafındaki?
For example, there is one over there in close to Emir. How many kilometers is Emir from here? Approximately. Something around 20, 30 kilometers. Let's just imagine the radio signals that it emits. Well, it is decaying with 1 over the distance. So let's say at this point of the classroom, that factor is 1 over 30 kilometers. And at the other end of the classroom, it is 1 over 30 kilometers plus 5 meters. So the amplitude is constant within this classroom. Even those signals within this classroom are just plane waves. So you can just take this to be a constant. But this sine omega t minus kx dependence of A will just cause it to be a plane wave within this classroom. So that dependence on A, the existence of the radiation field basically is what is telling us that there is a wave. Well, the wave doesn't also always have to be harmonic. So you can just create something like a Gaussian wave, which will travel in time. So that will just tell me that there was a non-zero acceleration for a finite amount of time and the acceleration stopped. But in any case, the signal is moving. So that is what we call the wave. Now let's go back to our pointing vector. And keep in mind again that all these quantities appearing over here, A and theta and delta, they're all defined at the retarded time, not at the current time. So here is what we will imagine. I'm interested in calculating how much power the charge emits when it is at this point. That is what I'm kind of trying to calculate. So to calculate that, what I do is, well, at that time it will emit some radiation, so that it will be emitting some power, that it will have a radiative power, let's say. So to calculate that radiative power, I will be considering a very large sphere at a very far away distance with a large radius fixed at this point. Its center is fixed at this point, at the position of my particle. I will just keep my time and wait for, the radius, let's say, is r over c. I don't know how long it will take, but I will just wait r over c. And after a time r over c passes, I will just measure how much energy passes through my surface. That energy will be the energy radiated by my charge when it was at this point. Well, of course, when that energy reaches my sphere over here, my particle will not be at that point, it will be at this point, but nevertheless, that power passing through my sphere will give me how much power is emitted by my charge when it was over here. Well, you can just put in the numbers and do the integration, and it turns out that the power is given by mu0 q squared a squared over 6 pi c. Well, q squared is already over there in that squared, and then we have this 1 over delta will be cancelled by this 1 over delta squared will be cancelled by the delta squared of the surface area. So this power is based nothing but S dot d, let's say A, over my surface. My surface area is delta squared. Well, there is a sine squared theta dependence, so you have to take that into account when you are evaluating that integral. And 6, that is 6. So this is the power at which the particle is losing energy at a given time. Let's say this is power at a given time. T is given by the acceleration at that time, t. You see, electromagnetic radiation does not radiate, but the charged objects, they radiate. This is the amount of energy that my charged object radiates. Well, this is the energy it loses per second, let's say, because it is radiating energy.
T mi yoksa TR?
Well, you see, it is at this expression, it is T. Why is it at T? Now, what we did, let's say we want to calculate, let's just choose the time T is equal to 5 seconds. Okay, so we want to calculate the amount of power my charge radiates at 5 seconds. Okay, so I imagine a sphere that has a radius, let's say 1 light year. So at 5 seconds, my particle is over here, and I assume that it is at rest at 5 seconds. Then it radiated some power. I wait for 1 year. Because the amount of power it radiated will reach my sphere, which has this radius of 1 light year, after 1 year. So I wait for 1 more year. At 1 year later, I determine what its power was at 5 seconds. So I calculate the power. This is the power at 5 seconds. That is the power at 5 seconds. This is not the time that I determined this power. This is the time that that power was emitted by my charge. So that is why both of these are at t. I determined this power at 5 seconds plus 1 year. So in a sense, if you want, relative to this 1 year plus 5 seconds, both of these times are retarded times. But both of them are retarded times. So I can just change the label if you want.
Hocam burada mesela delta'nın direction'ı t'ye dik. Ama t'ye dik değil. Fakat biz t'den ölçüyoruz.
You see, t doesn't have a direction. T is just a number, it's time.
Ama o pointe dik bir şey almıyor muyuz yüzeye?
No. You see, the power is radiated at every direction, more or less. But it's dominantly at the perpendicular to the acceleration. So if you would plot, let's say, if the acceleration of my charged object at that instant is in this direction, if you plot its magnitude as a function of, in this space, let's say, so you basically obtain a donut shape. Okay, this shape is kind of complicated. This is the surface. In this direction of the surface, the magnitude of the electromagnetic radiation is given by the distance from this radius. Now here is a point. The hole of the donut is just a point. So you can say that the amplitude is equal to this. Well, just normalize the amplitude. The radius from this point gives me the amplitude. So you see the distance of the surface in this in the direction of the acceleration is 0. There is no radiation in the perpendicular direction. The maximum is in the direction of the acceleration. The maximum is in the perpendicular direction. To calculate the total power, we are integrating all of them. We are summing all of them. So keep in mind this total power is the integral of the Poynting vector over all of the sphere. So I'm just integrating over all of this sphere. Some areas of the sphere does not contribute, some area contributes more than the other one. But I'm just summing them all up. That is why I have this expression. This is the power, the total power. Now there's a slight catch over here though. We are only calculating the radiated energy. But let's just imagine this object. Initially it was at rest, so it had an electric field but no magnetic field. Then it accelerated, so it started moving. It created also a magnetic field, and the electric field is also modified. Now, the magnetic field, for example, not all of the magnetic field is in the radiation field. Some of it is the radiated away, but some of it just stays with the particle. So now there's a non-radiated additional magnetic field. But this also means that there's some energy stored in this non-radiated magnetic field. Well, we know that magnetic field stores energy. Well, let's go back to our expression. This is the electric and magnetic field of a charge. No, not that one. This is the motion electric field created by a charge that is doing an arbitrary motion. You see, we are only considering this term. We are saying that this is the radiated field, this is the non-radiated field, because it goes as 1 over r distance squared. Well, this is the magnetic field. There is a corresponding magnetic field which goes as 1 over r squared. At infinity, they will not contribute to the Poynting vector. But nevertheless, some of the energy that we put in the particle will be transferred into this non-radiated electric and magnetic fields because its velocity is changing. So if we are only looking at the change in the kinetic energy of my particle, we should, in fact, to be more precise, we should take those into account also. But which we did not. Well, we can kind of get away with it if we calculate the total power from time t1 up to time t2. This is the total energy emitted by my particle. Now, these times t1 and t2, I will assume that at the time t1 and at the time t2, my particle has the same velocity. So that the magnetic field doesn't change, the electric field at the time, the non-radiated electric and magnetic fields at the time t1 and at the time t2, they are the same. Sure, but acceleration can be positive, negative, it can be pointing in different directions. For example, you can say that we are imagining a system which is doing some harmonic motion. It's accelerating all the time, but the motion is constantly repeating itself. So at many different times, it will have exactly the same velocity, it will be at the same position. For example, in such a motion, there will be this radiated energy, but there is also this non-radiated energy, but at the time t1 and at the time t2, they are the same. So the change in the kinetic energy of the particle at the time t1 and at the time t2 will be only due to this radiated energy. Yes. I will put a minus sign over there because it's lost by the particle. This should be equal to the force due to radiation dot V dt from T1 to T2. F dot V is nothing but the power of a force. Again, from mechanics. Well, let's see, from T1 to T2, F rad dot V dt plus from T1 to T2, mu 0 q squared over 6 pi c a times dV by dt, as a dot dV by dt in vectorial form. Well, what did I do? Well, this is basically acceleration. Now, why did I do that? I will do an integration by part in that term. I put a minus sign because this is the power radiated by the charge, so the energy change, the power lost in a sense by my charge is minus that one. From T1 to T2, F radiated minus mu 0 q squared over 6 pi c a dot v plus mu 0 q squared over 6 pi c a dot v from t is equal to t1 to t2, this is equal to 0. What did I do? I just made an integration by part over here. I wrote this as mu 0 q squared over 6 pi c a dot v minus, instead of the derivative of v, I take the derivative of a. So this is a dot. Well, I'm assuming that my particle is kind of doing periodic motion. Its state at T1 and T2, they are the same. So this term is 0. And I'm left with the first one only. Well, the simplest force that is consistent with this restriction, let's say, is that if the radiation force is mu 0 q squared over 6 pi c a dot. This is not a proof that this is, from this relation you cannot claim that this is the radiation back reaction force. But nevertheless, this force is consistent with the fact that this should be 0. Well, there are other ways of deriving this force. This is probably one of the easiest ones to obtain this force expression, and it works. But in alternative derivations, you still get the same result. And you even remove the restriction that it should be at rest. If you remove that restriction, what you would get is that this radiation force is mu 0 q squared over 6 pi c gamma to the 6 a squared. No, sorry, this is not the. Let me look at the expression of the force. Okay, no. This is the power.
Şimdi şu bulduğumuz force başlangıçta
Hold, let me just write this one first. Well, this is kind of the relativistic generalization of the power expression, and from which you can get a complicated radiation back reaction force. But in our case, for us, this will be kind of enough to discuss some of the problems with this force. This law will be valid in the limit of particles moving at small velocities. Even if the particle is not at rest at this instant, you see the correction to the power is proportional to 1 over c squared, v squared over c squared, and unless the particle is moving at relativistic velocities, that will be negligible, and this force will still be valid. Now, one problem appearing over here is, so this is probably the first time we see a force that is proportional to the time derivative of the acceleration. Yes, your question.
Bu kuvveti bulduğunuzda parçacık başlangıçta rest diye almış.
But accelerating. Well, let's see what will be the solution. If this is the only force acting on my object, well, that kind of contradicts our initial assumption that the particle is accelerating to start with. But let's just, for the time being, ignore that thing. Let's assume that there is no external force acting on my object. And we can also say, for example, that The particle was moving in one direction. There was some external force acting on it. Right at t equal to 0, let's say it is at rest. And we kind of let the remove the external force at that instant. Mass times the acceleration, let's just imagine a one-dimensional case. This is equal to mu 0 q squared over 6 pi c a dot. Or a dot is equal to a over, let's say, tau 0. Tau 0 being mu 0 q squared over 6 pi mc. All these coefficients I put in this constant tau 0. A of t is equal to a0 e to the power t over tau 0. Now we have a problem. You see, this is the case when there's no external force. But it is accelerating exponentially.
Does it violate Newtonian physics?
Now this is all Newtonian physics.
O zaman parçacık şöyle hareket ederken kendi elektrik alanında mı?
Well, let's see. This is kind of a problematic example because, well, you can say that if there is no external force, A0 was 0 to start with, so since A0 is 0, A of t is 0. So there's no really a problem. Let's add the external force. It can be a time-dependent force. Well, you can solve this acceleration also. A of t contains, let's not make the explicit derivation. You see, the acceleration at the time t now can be written as such an integral for an arbitrary external force. Do you see the problem with this expression? The acceleration at the time t depends on the force at later times. T prime is after t. So even just adding this external force creates even more absurd problems for us.
Yani şey mi ya, parçacık burada ama kuvvet bu noktaya geldiği zaman bir kalkıyor.
No, the force is acting always on the particle. But let's say that you are applying the particle and you say that you will be exerting a very small force now and a large force later on. The acceleration now depends on your large force later on. So that is kind of weird.
Normalde ivmenin o anki kuvvete bağlı aslında.
Now that is what we would expect. I mean, that is also what we call causality. The cause, that is the force, should come before the effect, before the acceleration. The force comes after the acceleration. That is not causal. You have the breakdown of causality.
So did we assume something?
No, the derivation is correct.
That doesn't make any sense.
Exactly, it doesn't make sense. Well, the problem seems to have its roots in the assumption that we are considering point particles. So that seems to be part of the problem, at least. And for example, in your book, I will not go over it. It looks at this force as, you see, how do you generate this force? The book, for example, takes this example of two charges. Q over 2, Q over 2. You have this charged object. You have these two charges. They are moving with some velocity v, let's say. So at a later time, they will be somewhere over here. But the force that this feels will be due to the retarded position of this charge. And the force that this feels will be due to the retarded position of this charge. So that is basically why you get this additional force. That is the claim in your book, at least. Well, with this derivation, you get half of the force. Not all of this expression, but half of it. And the book says that, okay, we are ignoring that each one will also be exerting force on itself. So that's kind of one of the problems. How can a point charge exert a force on itself? Because we already started by assuming that the force felt by a point charge is due to the electric and magnetic fields created by other charges. So a force on it cannot really exert a force on itself. That's the problem we are having over here. So if a charge exerts force on itself, it will be just start accelerating on its own without any external force. Well, there is no general consensus on the solution of this problem. The problem is known. It's a part of classical electrodynamics. And as I said, it seems to be related with the assumption of point charges, or in the case of such models where you assume that it's an expanded object, the problem seems to be related with the assumption that it is a rigid body. So what does a rigid body make sense in the relativistic cases? So that's kind of the problem. So here, this is D, and for a point charge in your book, it takes the limit D goes to 0. So at least in some papers, they claim that this is the problematic part. You cannot take that limit. Because basically, another problem that you see is that the mass of your object, let's say if it was neutral, its mass is m0. Now you add the potential energy. So this is kind of the effective mass of the object, it turns out to be. The potential energy between these two things. But the potential energy turns out to be infinite. So you have to assume that this m0 is to start with a negative infinite number. So there are problems. As I said, there is no general consensus on the resolution of this problem. So there's such a problem, let's say. Let me end it over here.
Yani bu hala çözülmemiş bir şey.
No.
Kuantumda mı çözülmüş?
Well, I mean, there are ways to just sweep this problem under the rug, so to say. Halının altına süpürebiliyoruz. But there is no general solution, no accepted solution. At least there seems to be no accepted solution that I could find. I found some papers written in 2005, 10 years ago, still discussing these problems.
İyi, güzel. Bize buradan ekmek çıkar.
Okay, last questions. I need to go, so you don't have too much time to think about your questions. In the second hour, your assistant will be here.